What if I told you that the sun were to magically disappear, the Earth would continue orbiting for about 8 minutes and 20 seconds. And this is because of gravitational waves. But what are waves? For example, let's look at sound waves. Sound waves is the compression and decompression of particles throughout a medium, transferring energy from one location to another without transporting matter. Now, gravitational waves. They differ massively in comparison to sound waves, and two simple and not so simple differentiating features is the fact that they do not need a medium to travel through, and they act upon matter differently. Noticeable gravitational waves form when a massive object has acceleration, such as two black holes having a binary orbit and growing closer to one another, and other massive changes in the fabric of space-time. Let's use this parachute as a demonstration. If a wizard were to conjure a random mass into space, a ripple would be emitted from that object. That ripple is a gravitational wave. In order for you to understand how they act upon matter, imagine that your eyes are emitting gravitational waves substantially stronger than the ones LIGO sent on September 14, 2015 onto these particles. And there we go. And slow it down a lot. You'll see that the ring is getting compressed vertically and stretched horizontally, then vice versa. But you cannot actually see this because this is occurring at the speed of light. Let's take a quick gander at interference. When two of the same types of waves interact with one another, they interfere. This interference can either be constructive, resulting in a higher amplitude, or destructive, resulting in a lower amplitude. Let's look at the two of these tuning forks. When I hit one, you get this noise. When I hit the other, you get another noise. When I hit both of them at the same time, you get to hear the two waves interfere with one another. The more quieter parts are when the crests of one wave line up with the troughs of the others. The louder parts are when the crests of each wave are lined up. The reason we went over interference is so that we would have a base to understand what an interferometer is. An interferometer produces data that we can analyze when a beam of light is interfered with, hence the name. So how do they work? Well, a beam of light is pointed towards a beam splitter. That then divides the beam into two equal and separate less powerful beams perpendicular to one another. Those then travel equal distances to get reflected back to the beam splitter and recombine. If there was no change in the distance it took each beam to travel, the combined beams would cancel each other out and no light would be produced. However, one or both of the beam's distances were to change. When they recombined, there would be an output of light. Now, where does that data come from? Well, the resulting beam is directed towards a solar cell, and when there's light, the solar cell will produce a charge. That charge is then processed into sound and becomes recorded data. Differing light waves would make different sounds, like this. Anyways, waveform analysis, it's when you analyze a waveform. A waveform being a shape of a wave at a given time. But why do you want to do this? For example, if you run YouTube and people are complaining about copyright infringement, so what they've decided to do is have people upload reference files to YouTube's Content ID database. Each file is a pattern. There are currently more than 50 million of these files. So when a video gets uploaded, it is processed afterwards. During this time, the Content ID database quickly runs through the video and looks for patterns. If a pattern matches up, the video gets instantly flagged for copyright infringement, and this entire process is waveform analysis. LIGO also uses waveform analysis. Instead of analyzing YouTube videos for copyright infringement, they analyze data produced from their interferometer for a specific pattern of interference. That pattern is what they predicted a gravitational wave would look like if one would hit Earth using computational physics. After a wave hit on September 14, 2015, they sensed a distance change of 1/1000th of the diameter of a proton over their 4-kilometer long arms on their interferometer, and the sound that was recorded is this. The amazing part about this discovery is that it was accepted within 5 months. I mean, it took 7 years for Thomson's discovery of the electron to be accepted into the atomic model. Again, 4 months later, they sensed another gravitational wave, hitting the Earth on June 15, 2016. But how do we know that these disturbances are not just vibrations on the ground? Well, the majority of their spendings went into preventing this, by keeping the mirrors of the interferometer to stay in the same position no matter what. They have achieved this by suspending the mirrors by 4 pendulums, each with differing lengths. If there was a vibration, the top pendulum may start swinging, but if it does, it will not resonate with the next one. If the second pendulum does not resonate, it will not swing. It may swing a very small amount though, but same rules apply. It will not resonate with the third one because of the varying lengths and no vibrations will be transmitted.